Today we will think together of a possible strategy to write observables as functional of a simple quantity. Of course, we know how to express things in terms of the many-body wave function, where expectation values are simply integrals. But we cannot calculate and store the wave function, so this is not our way of choice. In principle, we know that observables depend only on the external potential. And we know an explicit expression. But it is really too complicated to be useful. So the question is, can we find another simple quantity in terms of which we could express our observables? Let us look again at an expectation value, which is an integral over the many-body wave function. If our observable is described by a local one-body operator, then this expression simplifies. Since all electrons are equivalent, we can integrate over just one coordinate. Then we can rearrange a bit this integral, and we are left with an expression that contains the one-body operator and the one-body density, n, appears. So you see, we need only the density to calculate the expectation value of a local one-body operator. But what about the expectation value of a two-body operator? For example, the Coulomb interaction energy. I can do the same tricks as before. And now, out of the integral comes the two-body density, which is still much simpler than the full many-body wave function. What else might we be interested in? Another example, the kinetic energy. Again, we can easily express it in terms of the many-body wave function. This time, shuffling around the terms is not completely trivial. See, you have to make sure that the derivative is taken only on the wave function on the right side. So we introduce two different space arguments, x and x prime. And we make them equal only at the end of the calculation, after the derivative is taken. In this way, we can again separate the operator from a big integral, which is nothing else but the one-body density matrix. We could play this game forever. Say we are interested in spectroscopy, where we excite electrons, for example with sunlight. Then we will have still other things to calculate. A very important fact is that the system will make transitions to excited states. And this is why excited state wave functions will appear, here labeled by an index S. And because electromagnetic fields are oscillating, in general, even the time t will appear. This gives the wave functions a phase factor, an oscillation with the excitation energy, which is the difference between the ground state energy and the energy of the excited state. Again, everything else integrates out to a compact object, which will give us transition amplitudes. This is just to show you that the variety of expressions that may appear, all compact objects, but all different. Actually, it seems that we almost need a different compact quantity Q for every observable O. Sometimes the density, sometimes the one-body density matrix, sometimes the two-body density. Okay, you might say, why do we care? The important thing is that these are all simple expressions, no? Well, if you think about it, the problem is, up to now, we do not know how to calculate any of these quantities Q, not the one-body density, not the two-body density, not the density matrix, none of these. Unless, of course, we are willing to use the many-body wave function, and here the answer is no. So there is no free lunch. We will have to put some effort somewhere. Let us choose the problem that we are willing to solve. The first possibility, we stay with what we have just found. So we are willing to use a different compact quantity Q for every observable O that we are interested in. What we then have to find is a way to calculate each of these Qs, be it the density when we are interested in a one-body expectation value, or the density matrix for the kinetic energy, and so on. The second way to go is that we insist on the idea to have just one simple quantity Q that gives us all observables. Now, in this case, it is clear where some hard work goes. We still have to find the expression for our different observables in terms of this one elected quantity Q. And we should not forget that, of course, we also have to calculate that quantity Q itself somehow. But at least this problem has to be solved only for one Q. Between the two ways to go, this is the choice that we make in this course. You know, I think it is important to realize that we did have some choices on the way up to this point. Nothing is obvious. So, which Q do we choose? Well, since we opted for having a simple life with Q, let us choose the simplest one, the one that gives us directly the one-body expectation values. Then at least all those are simple. So from now on, instead of expressing observables as functionals of the many-body wave functions or of the external potential, we will search for functionals of the density. Up to now, we don't even know whether this is possible. Nevertheless, I hope that you are motivated to accompany us in this adventure. We will see soon what we can do.